Balloon 4-5 weather theory and reports. Navigating the skies as a balloon pilot means being attuned to the atmospheric irregularities known as turbulence. It's like the whimsical motion of the atmosphere, marked by those unpredictable gusts and lulls in the wind. This natural phenomenon can be a bit tricky, so let's dive into what causes it and how it behaves to help you steer clear or minimize its effects. Turbulence comes in different flavors, each with its own set of triggers. First up, there's thermal turbulence, which is like the result of a localized convective activity due to surface heating or cold air moving over warmer ground or water. Imagine the air having its little convective currents, some vertical, some horizontal. Then there's mechanical turbulence. Picture this: wind flowing over uneven terrain or flowing around obstacles, creating a bit of commotion in the air. It's like the landscape is playing a role in this atmospheric performance. Frontal turbulence is another player, brought on when warm air gets lifted by colder air masses or when the wind abruptly shifts associated with cold fronts. Lastly, wind shear is like the dramatic change in wind speed or direction, all thanks to some general vibrations happening in the temperature and pressure fields up above. What's interesting is that these causes often team up for a combined effect. It's like different factors taking the stage together, each with its own impact. Think of it as an updraft in a small-scale convective current. When the air gets cozy with a warm surface, it starts moving, creating vertical or horizontal currents. The strength of these currents depends on things like the type of surface. Bare, sandy grounds are more conducive to this atmospheric activity. So picture this scenario. You, the balloon pilot, caught in a thermal. You'll notice your balloon doing a bit of an unexpected ascent, and here's the trick. Without you needing to use the heater, the air mass is rising with your balloon and there's no significant pressure against the top of the balloon, so it won't pop its cap open. Now, some thermals may have a bit of a spin to them, like a mini low-pressure system showing off its unique characteristics. If your balloon gets caught in this twirl, remember, altitude is your friend. Make sure you've got enough height to clear any potential obstacles and keep the temperature right for level flight. Don't rush to descend. These thermals usually release the balloon at the top after a short time. Understanding these atmospheric irregularities, whether it's thermal activities or the coordinated chaos of wind shear, gives you the insight to navigate through the skies with confidence and safety. It's all about knowing the steps and making the right moves in response to the whims of the atmosphere. When the air near the Earth's surface encounters obstructions like hills, mountains, or buildings, it undergoes a bit of a transformation. The usual smooth, horizontal wind flow gets disrupted, giving rise to eddies and irregular air movements. Picture the wind playing around with the terrain, creating pockets of turbulence. The strength of this mechanical turbulence depends on factors like wind speed, the nature of the obstruction, the stability of the air, and the angle at which the wind interacts with the obstacle. Stability seems to be the star player here. It takes center stage in determining how strong and high this mechanical turbulence can go. Now let's talk about frontal turbulence. This one's a result of warm air getting lifted by a frontal surface, creating a mix or shear between warm and cold air masses. It's like a bit of atmospheric drama when these air masses clash. The severity of frontal turbulence kicks in when the warm air is moist and unstable. Fast-moving cold fronts usually bring the most intense cases of this turbulence, thanks to the mixing and differences in wind speed and direction. Now let's shift our focus to wind shear, which is like a steep change in wind velocity along a given direction, either vertical or horizontal. This change produces swirling motions, eddies, that lead to turbulence. Clear air turbulence, known as CAT, is its sudden and severe version that happens in cloudless regions, often associated with wind shear. Imagine it as a spontaneous turbulence in the open sky. Sometimes, during ascents or descents, a balloon encounters a narrow zone of wind shear at the top of a temperature inversion. These inversions can happen from just above the surface to the tropopause. It's like a balloon navigating through a zone of changing winds, adding a bit of unpredictability to the journey. Low-level wind shear is a bit of a troublemaker. It's a sudden and drastic change in wind speed and/or direction over a small area, making the balloon experience abrupt updrafts and downdrafts. This is especially risky near the ground, and low-level wind shear is often associated with passing frontal systems, thunderstorms, and temperature inversions with strong upper-level winds. Now let's talk about obstructions on the ground, terrain, and buildings. They can be unseen hazards, disrupting the wind flow and creating gusts that change rapidly. From natural features like mountains to man-made structures like hangars, these obstacles affect wind flow and pose challenges during takeoff and landing. Picture a balloon encountering turbulence, dropping in unexpectedly during the landing phase due to disrupted airflow around these obstacles. It's like navigating through a landscape where the wind behaves differently based on the terrain. Mountainous regions add an extra layer to this challenge. While the wind flows smoothly up the windward side of the mountain, creating upward currents that help carry an aircraft over the peak, things get a bit tricky on the leeward side. The downward flow on the leeward side can be turbulent, pushing an aircraft into the side of a mountain. The interaction between wind and terrain creates downdrafts in valleys or canyons, adding an element of unpredictability. So, as a prudent balloonist, it's essential to be aware of these atmospheric nuances and make the right adjustments, especially when navigating through challenging terrains or encountering different types of turbulence. Imagine a majestic mountain standing tall against the canvas of the sky, ready to showcase a breathtaking performance called the mountain wave. This natural spectacle, marked by rhythmic updrafts and downdrafts, unfolds when brisk air encounters the steep front of a mountain range. Now envision the air gracefully flowing along the mountain's windward side, gaining momentum until it reaches its zenith near the summit. Yet as the air glides over the crest, it transforms into a captivating display of downdrafts, creating a mesmerizing illustration of nature's prowess. The intensity of this mountain wave performance is truly remarkable, with records showing sustained downdrafts and updrafts exceeding 3,000 feet per minute. Turbulence becomes an integral part of the act, ranging from a gentle sway to a dramatic whirl, especially in the lower levels. Imagine the air, now 5 to 10 miles downwind from the summit, gracefully ascending in harmony with a distinct wave pattern. Additional waves join the ensemble, creating ripples in the sky, much like the downstream flow from a submerged rock in a swift river. The distance between these successive waves varies, providing a dynamic backdrop influenced by wind speed and atmospheric stability. But the stars of this show aren't just the air currents. Clouds also play a vital role. Enter lenticular clouds, smoothly contoured and formed by the mountain waves, taking center stage above 20,000 feet MSL. These clouds, resembling elegant lenses, may stand alone or layer up, adding a touch of drama when turbulence is in the air. The roll cloud, appearing near the mountain ridge's height, and the cap cloud, a turbulence-laden entity, play their parts, forming on the windward side and dissolving on the lee side of the mountain wave. Now let's talk about eddies or rotors swirling in the performance. These eddies can emerge within the mountain waves or form due to downslope winds, creating gusts or wind shear that add an extra layer of unpredictability. Clouds may even move within these rotors, further contributing to the atmospheric choreography. While researchers continue to unravel the mysteries of mountain waves and rotors, one thing is certain: pilots need to be keenly aware of these aerial displays and take appropriate precautions. Even though mountain wave activity is typically forecasted, local factors can influence the formation of rotors and eddies. Pilots, like astute spectators, should observe the signs, whether it's disturbances on water or fields or the formation of clouds, nature's way of hinting at the intricacies unfolding in the sky.